Welcome to G Fun Facts Online. We see them all the time, those colossal windowless jets lumbering across the sky. Cargo planes. They are the circulatory system of our global economy. The unsung workhorses that carry everything from your online shopping to life-saving medical supplies. But these heavy lifters operate under pressures far beyond what passenger jets ever experience. Their world is one of immense physical forces, razor-thin margins for error, and unique engineering risks that push materials and design to their absolute limits. Today we're going under the skin of these giants to uncover the hidden dangers and the incredible engineering required to keep them flying safely. The very purpose of a cargo plane is to carry immense weight. But that weight isn't neatly distributed like rows of passengers. We're talking about multi-ton pallets, industrial machinery, even military vehicles. This puts incredible, concentrated stress on the aircraft's structure. Imagine the main cargo deck. In a passenger plane, the floor just has to hold up seats and people. In a freighter, that same floor is replaced with massively reinforced aluminum beams, a structural backbone designed to withstand the crushing weight of unit load devices, or ULDs, which can weigh several tons each. The sheer weight of the cargo also creates huge bending forces on the entire fuselage, especially over the wings. Get it wrong, and the plane could literally break its back in mid-air. That's why manufacturers have strict limits on how much weight can be accumulated in any one section. But perhaps the single biggest structural headache is the main cargo door. To load all that bulky freight, you need a giant hole in the side of the plane. From an engineering perspective, a hole is the last thing you want in a pressurized tube. It's a massive point of weakness. This cutout creates huge stress concentrations, making the area around the door a prime suspect for metal fatigue, tiny cracks that can grow with every single flight. The door itself has to be a masterpiece of design, strong enough to hold back the immense pressure difference at 30,000 feet, but light enough to not cripple the plane's carrying capacity. Early cargo door latches were a notorious point of failure. In 1989, an Evergreen DC-9 crashed because the main cargo door wasn't latched properly and blew open after takeoff, leading to a catastrophic loss of control. It's a constant battle between access and integrity. And as these planes age, flying for decades, the invisible threat of metal fatigue becomes ever more critical. Inspectors use advanced techniques to hunt for these tiny cracks before they can grow into a disaster. Structure is one thing, but balance is everything. For any aircraft, the center of gravity, or CG, must be within a very specific range for the plane to be stable and controllable. For a cargo plane, this is a monumental challenge. One of the most terrifying risks is cargo shifting in flight. This isn't a theoretical problem. On April 29, 2013, National Airlines Flight 102, a Boeing 747 freighter, took off from Bagram Airfield in Afghanistan. Its cargo included 5 massive, 18-ton mine-resistant ambush-protected vehicles, or MRAPs. During the steep climb, at least one of these behemoths broke loose from its restraints. It slid backward with incredible force, smashing through the rear pressure bulkhead and severing critical hydraulic lines and flight control systems. The aircraft's center of gravity shifted catastrophically in an instant. The pilots had no chance. The 747 stalled and plunged to the ground, killing all 7 crew members. An investigation found that the airline simply hadn't used enough straps to secure the incredibly heavy vehicles. Even when cargo is secured, a simple calculation error on the ground can be just as fatal. A study found the risk of a weight and balance-related accident is over 8 times higher for cargo flights than passenger flights. Why? Because while passenger weights are often averaged, every piece of cargo must be weighed and its position meticulously planned. A center of gravity that's too far forward makes the plane nose-heavy and difficult to lift on takeoff or landing. But a CG that's too far aft is even more dangerous. It makes the aircraft tail-heavy and violently unstable. This is what happened to Emery Worldwide Flight 17 in the year 2000. The DC-8 cargo jet was loaded incorrectly, placing its CG far behind the safe limit. The crew fought for control right after takeoff, but the plane was inherently unstable. It crashed, killing all 3 crew members. The balancing act for these heavy lifters is a high-stakes affair, where a misplaced pallet or a data entry error can have the ultimate consequence. Imagine a fire starting inside a sealed metal tube at 35,000 feet. It's one of the worst-case scenarios in aviation, and in a cargo hold the risk is magnified. The hold is packed with a random assortment of goods, a veritable tinderbox. But the biggest modern threat comes from something we all use every day: lithium-ion batteries. Found in laptops, phones, and increasingly electric cars, these batteries pack a huge amount of energy. If damaged, they can enter a state called thermal runaway. This isn't just a fire. It's a violent, self-sustaining chemical reaction that generates intense heat and can spread from one battery cell to the next, like a chain reaction. Worse yet, the standard fire suppression systems on aircraft are often useless against it. Most planes use halon gas, which works by smothering a fire, robbing it of oxygen. But a lithium battery fire generates its own oxygen. Halon can't stop the internal chemical reaction. The tragedy of UPS Flight 6 in 2010 is a stark reminder. A fire started in the main cargo hold, triggered by a large shipment of lithium batteries. The blaze produced thick, toxic smoke that quickly overwhelmed the cockpit, obscuring the instruments and incapacitating the pilots. The Boeing 747 crashed near Dubai, killing both crew members. The investigation revealed a terrifying gap in safety. The lower cargo holds on most planes are Class C compartments, meaning they have both smoke detectors and a fire suppression system. But on many freighters, the vast main deck is a Class C compartment. Regulations don't require a fire suppression system here. The strategy is to simply depressurize the cabin and hope the lack of oxygen starves the fire. Against a lithium battery blaze, this is a losing battle. It's a regulatory loophole big enough to fly a 747 through, and one the industry is still grappling with today. With the boom in e-commerce, the demand for air cargo is insatiable. The solution? Take an old passenger jet and give it a new life as a freighter. This process is called a passenger-to-freighter, or P2F, conversion. It's a complex, surgical undertaking. Engineers must cut that giant cargo door into the fuselage, meticulously reinforcing the surrounding structure to compensate for the weakness. They rip out the passenger seats, galleys, and overhead bins, and install a brand new, heavily reinforced floor with a cargo loading system. A rigid 9G barrier is installed just behind the cockpit to protect the crew from the terrifying possibility of shifting cargo we discussed earlier. Once the physical work is done, the converted aircraft must go through a grueling certification process to get a supplemental type certificate, proving to regulators like the FAA that it is just as safe as when it was first built. But this process itself introduces risks. The human factor is huge. Maintenance is a high-pressure job, and mistakes can happen. The industry even has a name for the common causes of these errors: the dirty dozen. These include things like complacency, fatigue, pressure to work quickly, and lack of communication. An improperly torqued bolt or a forgotten connection from a maintenance check years ago could be a ticking time bomb. The crash of American Airlines Flight 191 in 1979, where an engine fell off during takeoff, was traced back to improper maintenance procedures. For a converted freighter, which has been fundamentally altered, this diligence is more important than ever. The world of cargo aviation is a story of incredible engineering triumph against immense physical challenges. From the microscopic threat of metal fatigue to the kinetic fury of a shifting 18-ton vehicle, the risks are unique and severe. The tragic crashes of National Airlines 102, UPS Flight 6, and Emery Worldwide 17 weren't just disasters, they were brutal, invaluable lessons written in wreckage. They forced changes in regulations, in loading procedures, and in how we handle hazardous materials. Looking forward, as we demand ever larger aircraft to feed our global supply chains, engineers will face even greater challenges, like the fundamental square-cube law, which dictates that as a plane gets bigger, its weight increases much faster than its wing area. This will demand radical new designs and materials, but the core principles of safety, learned through decades of experience, will remain paramount. So the next time you see one of those giant windowless planes gliding overhead, remember what it represents. It's not just a flying truck. It's a marvel of structural integrity, a perfectly balanced machine, and a testament to the engineering ingenuity required to keep the heavy lifters of our world safely in the sky. Thanks for listening to G Fun Facts Online.